Hey guys, Bidish here. In this video, we're going to discuss waves with respect to 9th standard physics. First, we'll see what is a wave, then we discuss the types of waves, followed by their properties and phenomena related to waves. Since our focus is on 9th standard physics, we'll focus mostly on sound waves. So let's dig right in. So, what exactly is a wave? When I say the word wave, probably what comes to your mind is something like this, or maybe something like this. But wait, is that it? Now that's more like it. As you can see, a wave is a pattern which moves. So let's see the theoretical definition now. You see, a wave is a pattern of disturbance which moves without actual physical transfer of matter. Of course, this is to transfer energy. Now, it is produced by a vibrating object, which is basically an object which is undergoing to and fro motion. At this point, you're probably going like, whoa, Bidesh, slow down. That was a bit too theoretical. Well, no need to worry, my friend, because in real life, waves are everywhere. Examples include the ripples which are created on water when you throw a pebble into it, to sound waves, which is why you're able to hear me right now, to radio waves, and right up to light waves, which allow you to see. There is, however, a very important concept to be addressed here. You see, the waves on the right-hand side of the screen, that is the light waves and radio waves, are electromagnetic waves, whereas those on the left-hand side are mechanical waves. Mechanical waves do need a medium for propagation, whereas the electromagnetic waves or EM waves do not need a medium for propagation. That's all you need to know right now. For now, we will be focusing on mechanical waves with more emphasis on sound waves. Now, mechanical waves are of two types, namely transverse waves and longitudinal waves. Examples of transverse waves include ripples on a water surface or a wave created by a rope by to and fro motion of your hand. Well, basically, you swing the rope like that. Can you guess what an example of a longitudinal wave will be? That's right, it's sound itself. Now, in case of a transverse wave, the direction of oscillation of matter particles is perpendicular to the direction of propagation of wave. As you can see here, the rho particles are oscillating in a vertical manner, whereas the wave is propagating in a horizontal manner. However, in the case of a longitudinal wave, the oscillation of matter particles is parallel to the direction of propagation of wave. Here, the diaphragm of the speaker oscillates in such a manner which causes the particles to also oscillate in a horizontal manner, and as we know, the wave itself is propagating in the horizontal manner. Now, recall what we learned about mechanical waves. They need a medium. Can we find out what the media are in these examples? Of course we can. You see, the media for the transverse wave in this example is the rope, whereas for the longitudinal wave, that is sound, is air. Note, however, that the medium for air can also be water or any other liquid or even a solid through which sound can propagate. The source in these cases, if we look at them, are to and fro motion of hands for the transverse waves and oscillating diaphragm of the speaker for the longitudinal waves. In both cases, as you can see, they are oscillating objects or vibrating objects, just as we studied. Now, let's look at sound waves in a bit more detail. You see, compressions are the regions of high pressure where particles are crowded together and these are represented by the upper portion of the curve. Let's label these areas C. Then you can see that the upper parts, the peaks, denote the maximum compression and are called crest. Similarly, the rarefactions are the regions of low pressure where particles are spread apart and are represented by the lower portion of the curve. Let's label them R. These lower portions, the valleys, represent the areas of maximum rarefaction and are called troughs. So that's all about it for the sound waves. Let's now go into a bit more. This is what a typical wave looks like, as we saw. The upper parts are called crests and the lower portions are called troughs. Along the y-axis, we have either the particle displacement as in transverse waves or density of medium as in longitudinal waves. Now, we'll encounter a few characteristics of waves. Be warned, the next part is extremely theoretical and I'll just glance through the main points. You can pause the video and review them at your leisure. First, we have a wavelength. Wavelength is the distance between two consecutive compressions or two consecutive rarefactions. Then we have frequency, which is the number of oscillations per unit time. Note, however, that the oscillation basically refers to change in density or displacement of particles from maximum value to a minimum value and then back again to the maximum value. Next, we have got time period, which is basically time taken by two consecutive compressions or rarefactions to cross a fixed point. This can also be stated as the time taken for one complete oscillation. Finally, we have amplitude, which is the magnitude of maximum disturbance from the mean value. It is usually represented by A, and of course, the loudness or softness of a sound is determined basically by its amplitude. Cool. Next, we see speed. Speed is defined as the distance which a point on a wave, such as compression or rarefaction, travels per unit time. We know that speed is equal to distance divided by time, and this follows from the definition v is equal to lambda by t, where lambda is the wavelength distance traveled by sound in one time period of the wave. Rewriting 1 by t as nu, we get v is equal to lambda nu, that is, speed is equal to wavelength times frequency. The speed of sound remains almost the same for all frequencies in a given medium under the same physical conditions. Whew, that was a lot of text. Let's go back to some nice graphics. Now coming back to the picture of the typical wave that we saw before, here we can see that the wavelength of this wave is as follows. Of course, the amplitude is also as this. Now, let's try to apply what we learned to the waves we saw at the beginning of the video. Here I have a table to compile what our observations. Now let's say I draw an arbitrary line here. As you can see, there are more crests of blue waves passing it per unit time than that of the red wave. Hence, I can conclude that the frequency of the blue wave is higher than that of the red wave. However, at the same time, this means that the red wave has a higher time period since more time is taken by consecutive crests to cross the green line. Amplitude of the blue wave is visibly more than that of the red wave. However, in the case of wavelength, we can see that distance between successive crests is more in case of the red wave. Cool. Now, you might say, that's all fine, Badish, but how is it that we differentiate between, say, a violin and a flute producing sound of the same frequency and amplitude? Well, my dear friend, this is due to such characteristics as timbre and pitch. Pitch is how the brain interprets the frequency of sound, whereas timbre is a characteristic which helps us to distinguish two sounds having same pitch and loudness. The sound which is more pleasant is said to be of a rich quality. Now, we're going to look at some properties of waves. You see, first we have reflection, next we have superposition, and third we have speed in different media. You do not need to worry about superposition since you will be studying about it in higher classes, and reflection is pretty straightforward. Just like sound bounces, a rubber ball bounces off a wall, sound bounces off the surface of a solid or a liquid, and this occurs following the same laws of reflection as that of light. Okay. As for speed in different media, we note that the speed of sound depends on properties of the medium such as temperature and density through which it travels. You do not need to memorize the different values, but just keep in mind that under different conditions, speed in the same medium are different. So, now we'll look at some interesting phenomena of sound waves. This part is particularly my favorite. You see, first we have echoes. If we produce a sound, say a clap or shout near a suitable reflecting object such as a tall building or mountain, we'll hear the same sound again a little later. This sound we hear is called an echo. Now suppose this is you and this right here is a cliff. Now if you say, shout out loud, "You're awesome!" Guess what? After some time, you hear it back. Turns out, what goes around does come back around. Getting a bit serious though, since the sensation of sound persists in our brain for about 0.1 seconds, that is called the persistence of sound, we have to hear distinct echo, the time interval between original sound and reflected one must be at least 0.1 seconds. Now applying suitable assumptions and doing the required math, we find that the minimum distance from reflecting object to hear an echo should be 17.2 meters. However, this distance will of course change with the temperature of air. The rolling of thunder is caused due to successive or multiple reflections of echoes from between the clouds and the ground. The next phenomenon we study is reverberation. You see, a sound created in a big hall will persist by repeated reflection from the walls until it is reduced to a value where it is no longer audible. The repeated reflection that causes this persistence of sound is called reverberation. It is high reverberation is extremely undesirable, and hence you might notice that auditoriums are covered with sound absorbent materials. That's about it for this video, my friends. Thank you for watching. I hope you guys enjoyed the video. Give a thumbs up if you liked it. Cheers, and this is Bidish signing off.